Today I'm as here as a representative of Mahindra University pursuing MTech case. Okay. Today we're going to discuss how to determine the exact nature frequency of a structure, which is supervised by Dr. Visalakshi Menon. Okay, introduction. As we know, all the objects, when they are disturbed from its resting position, they tend to vibrate, and these vibrations are done in a particular frequencies, and these set of frequencies are known as natural frequencies. Okay, why the natural frequencies are important is these natural frequencies determine at which particular frequency the system tends to oscillate. By knowing these natural frequencies, we can prevent any of this system from oscillation. Okay, the purpose of this research is to find the natural frequencies and the mode shape of the structure, and to prevent the building from the resonance and tune the building in a more better way as possible. Okay, for the materials required, we use a PZT sensor and oscilloscope and drop hammer and vernier calipers for the measurements, and copper wire and plates for the preparation of the model. Now, methodology: first we go into numerical modeling, then experimental analysis, then comparison of this data. For the numerical modeling, first we have to find the stiffness of the structure. Once we find the stiffness of the structure, then we can write a MATLAB code to find the nature frequency and the mode shapes. Okay, to determine the nature frequencies and mode shapes of this structure, we have used an eigenvalue problem and a lumped mass system. Okay, the dimension of the model is as follows: as the height of the structure is 80 mm, for the each floor is 80 mm. The dimension of the slab is 147 by 157. Thickness of the slab is 1.2 and diameter of the column is 2.1. By doing this, we have get a numerical model analysis, and these are the mode shapes and the frequencies of the structure. Okay, the mode shapes as are given in radians per second, and this is how a system tends to oscillate. Okay, for the experimental procedure, we are using a gravity hammer. So gravity hammer is a drop hammer. So we'll be measuring a particular height, then we'll be dropping some particular weight on top of the structure where you want to give the excitation. Okay. Now let's look into how the experimental procedure is done.
We have prepared a 3 days plan. Okay. Then we bonded the sensor to the first floor over here, and we used epoxy for the bonding agent, and we have soldered these wires to the positive and negative terminal. Once the soldering is done, we have put an epoxy layer on top of it to prevent it from any further ruptures. Now, from this we are going to collect this 3 excitations point from the first floor, 1, 2 and 3, as we divided over here. So for this excitations collection, we are going to use drop hammer as we discussed. So the drop hammer length we have decided is 27 centimeters, which comes until over here. From here we are going to drop this ball weight of 44 grams. Then we are going to drop this and collect the data response over here, then feed the response. Collect the data over here, then feed the response to this pen drive. Then once we collect this data from this all 3 data sets, 3 responses, then we go into analytical modeling in MATLAB.
Alright, after collecting this data, we look at the response function, response versus time graph. As this response versus time graph is too clumsy, let's zoom and look into it. Okay, so this is the response of the structure when you have applied a particular amount of force. Okay, so we can calculate the FRS function by response by force. Okay, these FRS function plots versus the frequencies at which each node excitation happens. Okay, to find the mode shapes using FRS function, we have to pick one particular frequency in each excitation node, H12, H12, H13, and then we can plot these mode shapes. Okay, so these are the mode shapes of an experimental model analysis. So as we can see, there is a huge difference in the mode shape when compared to the numerical model. We can have a closer look into that. Okay. So the first three modes of the mode 1, mode 2, mode 3 are the numerical modeling, and the last three mode shapes are the experimental modeling, mode 1, mode 2, and mode 3. As we can see, there is a huge drop in the nature of frequencies and also the way these responses of the structure is happening. Okay. So in conclusion, the numerical modeling is a perfect state of the structure. Okay, so these mode shapes also will be perfect. Okay, and when you design and construct a building, these structures have some eccentricities present in it. Due to these eccentricities, and there will be a lower nature frequency compared to the numerical model. So in the real life utilization, by using these PZTs after construction of the structure, we can tune any of the structure. We can even use overhead water tank as a tune mass damper, tuning each and every second to make sure the structure won't resonance but it oscillates. Thank you for your time. Hope I see you guys next time.